Welcome to qnawire.
Okay, so here you have a firefighter that's sliding down this pole here, and you're told that the pole in total is 4 meters long. This firefighter is about 75 kilograms, and you're told that it's a 300 Newton frictional force acting on this system. Um, and you're told that he lands on a platform that is 20 kilograms, and that platform is supported by a spring that it has a spring constant K of 4,000 newtons per meter here. So essentially, you want to calculate the velocity that it hits the platform with, and then after that, you want to see what kind of compression it induces with that velocity. So the first thing is first, we want to find out how much speed this guy has when he gets to the bottom. So essentially, this is a second law problem. So you have the force of gravity minus this uh, this frictional force here. This is summing up all the forces that should give you the resultant force, which is mass times acceleration. So these are the two forces acting on this person as they slide down. So you notice that this we can calculate. This is just 75 times 9.8 minus 300, and then you divide that by the mass of the person, which is just 75. So once you do this, you actually find the acceleration, and the acceleration in this case is about 5.8 meters per square second. And then what you want to calculate now is um, so once you have that, now we want to find the velocity once they hit the bottom. So we know that we don't have anything in terms of time here, so we want to use kinematic equations that don't involve time. So the best one to use is that one that says v final squared is equal to v initial squared plus 2a times a change in distance, in which case the change in distance here is just y. So we know that the v initial here is 0 because we're told that it starts from rest. We assume it starts from rest if we are not told that. So this a is what we just calculated here. So that goes here, and then this delta y is the 4 meters over here. So we know that the final velocity is going to be the square root of 2 times the acceleration, 5.8 times the distance, which is 4. And that should give us something like 6.81 meters per second. Okay. So then the more complicated part of this problem is actually figuring out how much this thing drops by. So we can't use kinematics in this scenario because we have several different things going on. But the key here is that you're told that the frictional force acts throughout the motion. So you already have a hint there that you can't ignore the frictional force. And then, so once this guy hits this platform, both the platform and the person are going to compress the spring. So we need to essentially use uh, the conservation of energy to try and see if we can come up with a solution for this. So we know that he has kinetic energy. So he has half m v squared, where v is this v here, v final. And then we know that this mass is going to drop, which means it's going to, this potential energy change that is related to the compression in the spring. So we know that the energy, um, that there is some potential energy that he has as well before the compression. So that's going to be m G times the maximum compression that he's going to get, which is going to be Y. Because once you change the potential energy, you're going to convert that into some kind of compression energy that the spring has. And then we know that there's still a frictional force acting, pointing upwards, so that also has to do work on the system. So that will take energy away from our system. So that's going to be 300. But the energy is force times the distance. This is work done by the frictional force. So we know that we're going to multiply that by Y, because that's the distance that the frictional force is going to act to slow this thing down, starting from here. So we're starting our analysis from this point here. We could start up here, but in this case, we are starting down here. And that is now equal to the maximum spring potential energy that this thing is going to gain. And that is given by half k y squared. So notice that all of this so this is a known quantity, this is a known quantity, and this is a known quantity. So you only have a quadratic equation here that you need to solve. So now we have to look at the masses here. So this is actually the total mass here, and here's why. So once the person is sitting on this platform is going to go down, but the compression is actually being caused by the total mass of the person and the platform. So this mass is not the same as this. This is the total mass of the system. So once we do that, we'll notice that this equation actually ends up being something like 1740 is equal to so this is now negative 631 y plus 2000 y squared. So this whole expression is 75 plus 20 times g 9.8 minus 300, which will give you 631. Then you move that 631 becomes a negative, and then this is half of k is 4,000, so half of k is 2,000, and then you come up with this quadratic equation. So then you can just solve that in your calculator. You get two solutions. So y is equal to 1.1 or 0.79. So this is a negative value, but they want the maximum, so it's going to be this 1.1 meters here. That's the maximum compression that the spring gets.